Hello and welcome to Chem Tutoring for Basic Chemistry. This video will serve as an introduction to chemistry for students who are either in middle school or high school and are basically just starting off their chemistry career. This also works for students who are in college and are required to take chemistry courses, or students who haven't taken chemistry in a while and just need a refresher. This video will give you a short introduction to what you need to know and what you can expect in your coming chemistry courses. So we're going to start off here by looking at a periodic table. You're going to see a lot of these obviously, and we're going to start off by looking at the element of chlorine. So right away we see the atomic number, the name, the symbol, and this isn't super important, we'll learn this later on, but the chemical group block. So we can forget about the chemical group block for now and look at the atomic number. So right away we can tell that chlorine has an atomic number of 17. 17, and that tells us that there's 17 protons. So we know that there's 17 protons in chlorine. This usually means that there's also 17 electrons. And we can find the number of neutrons by subtracting the atomic number from the mass number. Now in this case, my periodic table doesn't have mass numbers. It was kind of hard to find one with mass numbers and clear out looking elements. So you want to find one that does have mass numbers. It's easier and it makes life easier. But I can tell you that chlorine has a mass number of 35. And then we subtract the atomic number from that, and that gives us 18. And we know that chlorine has 18 neutrons. So that's just a quick short introduction to how to read atomic numbers and find the protons, electrons, and neutrons from that number. Now looking at the structure of the periodic table, we always know that for the most part, we're going to find your metals around this area right here, with the exception of hydrogen. And your metalloids that run down here. And typically this last part is going to be your nonmetals. Now, we also have to note that the last column in group 18 is going to be your noble gases. These are the most stable form of atoms. They have 8 valence electrons. They're just very stable, they're very noble. That's why they're called noble gases. And the group next to it are called halogens. Now halogens only have 17 valence electrons on the outer shell, and they want to be as stable as noble gases, so they're going to try and get one additional electron most of the time to try to be as stable as the noble gases. So halogens only have 17 valence electrons. We'll look at that later on though. We're going to do a little practice just in a second just to get you with the right idea. Now, that kind of gives you the basic idea of what the periodic table looks like and what to expect when you're looking at one. If we go into this test right here, this is just a college level introductory test. It's basically a placement test to see where you're going. I'm going to do some problems on here, but not all of them, because if we do all of them, it's going to take forever. And there's also some topics on here that are a little too advanced, I think, for the first video. So I'm going to be skipping some and then going into detail on others that I think are kind of relevant for basic chemistry. So starting off with number 1, we're looking at the number of significant figures and the number 3005. Now, significant figures are super important. You're going to use them basically whenever you're finding anything in any problem in chemistry. So it's super important that we learn how to do that. Now, significant figures, in this case, I can tell you right away, there is 4 significant figures in here. And we're going to go over it later, but the reason why there's 4 is because in 3005, 5 is the last number in this number, meaning that it's a significant number, and there's 4 significant figures. Zeros that are in the middle of a number are always significant. However, zeros that are on the last part of the number are not significant, unless there's a decimal. If there was a decimal here, it would still be 4 significant figures. Without a decimal, though, this is 2 significant figures. As far as decimals go, significant figures count for numbers that don't start with a 0. So right here is only 2 significant figures, whereas this would be 4 significant figures. Also, we use it as a custom to put a 0 before any decimal, even if there's no number before the decimal. That also doesn't count as a significant figure. There's some more to this, but I think we can cover that in another video. Significant figures are typically pretty important in chemistry. So we're going to skip number 2 just because I feel like it's going to be very time consuming and we're going to go over conversions later on. So what is true about potassium? So if we look at potassium, let's go back to our periodic table. We can see that potassium is going to be right here. Now potassium is in group 1 because of right here. It's a metal, and for future reference, it's highly reactive with water, and it has 1 valence electron in its outer shell. So let's go back to our practice test and go back to that question. What is true of potassium? Well, we know right away that we said it was a metal, so it can't be A. It's a group 1 element, so it's not B. It's also not liquid at room temperature. Potassium is actually solid. I just told you that it's reactive with water because all the metals in group 1 are super reactive with water. So that's untrue. Potassium is very reactive. Now, Lewis dot structure, we'll go over them later on, but it's basically when you have the symbol for the element and you use dots to represent valence electrons on the outer shell. However, I told you earlier on that potassium only has 1 valence electron, so it only have 1 dot, making E our correct answer. Okay, millimeters. So this is again conversions. I'm going to go over it very quickly because I'm going to make a video later on explaining it in more detail. But millimeters to meters, not super hard, but we're also going to have to learn how to do scientific notation, and we can use this problem to go over that very quickly. So 33 millimeters into meters. Now, there's technically a conversion factor to use here, but for the sake of time and just to make it easier to understand, I'm going to draw it out for y'all. We're looking at a meter, like a meter stick. We have 10 millimeters, 3, 4, 5, 6, 7, 8, 9, 10 per centimeter. That's 1 centimeter. Now, we have millimeters to centimeters, which makes it 33 millimeters is going to be 3.3 centimeters. Now, centi means 100, and meters is just basically looking for 1. So what we'll do here, is take the decimal on the 100 for centimeters, and we're trying to get to 1, we're going to move it twice. So we go from 3.3 centimeters, moving it twice to the left, 1, 2. Now we have 0.033 meters. So we can get rid of these. It's not this one, it's not this one. And looking at the first two, we're going to write this in scientific notation. So if we move this scientific notation, we're always trying to get a number that looks like this, followed by an x to the power of, times 10 to the power of something. So we're going to move the decimal 1, 2 times to get that number, -2. This is our answer right here. Now let me note real quickly that if our number was, and we were trying to get, when we're trying to get 3.3, we move it to the left twice, and that'd be a different story. We'd have 3.3 times 10 to the power of +2, because it was a number greater than 1. Because this is a number less than 1, we're going to have a negative number here. So our answer is 3.3 times 10 to the power of -2. Okay, we're going to skip this next one just because, again, this is conversions and it's a longer video. Okay, what is true about isotopes? We went over isotopes earlier on in this video, and we can answer it based on what I told you earlier. There are different forms of an element differing in mass. This sounds like what I said, so let's just put that right there. They're always radioactive. That's untrue. Isotopes they can be radioactive, but they're not always radioactive, so that's untrue. Hydrogen has no isotopes, also untrue. There are different forms of an element differing in number of electrons. That's not true. Isotopes have the same number of electrons always, and none of these. So the answer is A. Okay, so now we've gotten to another topic that is kind of important to go over, so we're going to go over it very quickly. This is oxidation numbers. So, oxidation numbers are when you see a plus or minus sign. Sometimes it's followed by a number. It can look like this, like this, like this, like this, like that. You have the right idea. It's just a positive or negative number to the top right of an element. So right here, sodium has oxidation number of +1. When it's +1, we don't need to write the 1. It's kind of a given that the 1 is there. Just a positive is fine. So the total number of electrons sodium has is sodium with an oxidation number of +1. So the way oxidation numbers work is we have, we have sodium right here, and it's in group 1. Now, like I said earlier, the outer shell of the electrons, or the elements, are always trying to be at a perfect 8, and sodium doesn't really like having that one extra valence electron on its outer shell. It's not convenient. Let's just say sodium's not comfortable. He wants to get rid of it, so he's going to give it away. Usually, he wants to be like a noble gas, right? So he wants to give it away. That way he has that perfect outer shell. So elements on this group are typically trying to give away, with the exception of hydrogen. Hydrogen doesn't really have much to give away, it only has 1. So the metals in this group are trying to give away their electron, whereas the nonmetals in this group, halogens, are trying to get that additional electron. So what sodium is going to do is, when it has an oxidation number of +1, it's losing an electron. So sodium +1 has 10 electrons. Why is that? It's because usually it has 11 electrons, we can tell from the atomic number, but because it gave away 1, we can tell with the positive sign, it has 10 electrons now. So we can go back to our question, and our answer is 10. Which of the following elements would have the most similar properties to bromine? So when looking at properties, we can see the properties of an element. Sorry, let me erase this real quick. Okay, we can see the properties of an element by the group number. So we're looking at bromine right here, and atoms with similar properties are going to be atoms that are below it or above it. So halogens. We're looking for halogens. So iodine, chlorine, fluorine, astatine, and tennessine. Sorry, you don't really use those elements very often, so it's kind of hard to see what they are. But those are the elements that are going to have similar properties. Let's go back to our practice test. So we know that sodium is on the complete opposite side. Not going to happen. Argon's a noble gas. That's sulfur. Sulfur is not in the same group, and beryllium is on the other side of the periodic table. Chlorine, let's go back and look, should be a halogen, and it is. Look, it's right there. So chlorine is going to have very similar properties to bromine, and we can answer that question. The answer is chlorine. Choose the most stable ion for oxygen. So again, ions are when elements have oxidation numbers, and right away we can rule out that oxygen doesn't make ions because I can tell you right now, it does. So it's not E. We can also rule out 2 more when I tell you that basically when we're looking at the periodic table, elements that are going to be on this side are negative numbers, whereas elements that are on this side are positive numbers, or positive oxidation numbers. When we get to carbon, though, it gets a little more complicated because it's right in the middle. You get 1, 2, 3. So 1, oh, sorry, I have to reload there. We have 1, 2, 3, and then 1, 2, 3. So the 4th column right here, it's kind of funky, you know? But we don't have to focus on that right now. We can just say that we're looking at oxygen. So oxygen's right here, and we see that it is 1, 2 away from the noble gases, 2. And we know it's a negative number, so we can go back to our practice test. And we know it's a negative number. Oxygen is not going to be positive because it's on the right side of the periodic table, so we can cross these two out. And it's 2 away from the noble gases, so the answer is 2 minus. 2 minus, typically that's how oxidation numbers are written, with the minus sign after the number. The formula for the compound made from calcium and sulfur is, now there's a very easy way to do this, but we're going to leave this for another video because this can get kind of complicated and it kind of depends on where the element is located on the periodic table, so we're going to skip this for now. Now, the charge on phosphate is, again, this is having to do with nomenclature and knowing your molecules. Phosphate is PO4, and later on you'll learn that it has an oxidation number of 3 minus or minus 3, which is D. That, though, is for another video. It's okay if you don't know it right now. We'll figure it out later. So, draw a Lewis dot structure. I don't like the way this question is formatted. I didn't write this test, but I think it's kind of irrelevant to what it's asking. I feel like the Lewis dot structure is kind of deceiving because this right here isn't a Lewis dot structure. So, or actually it might be. Sorry, I'm just mixing my words up. Anyway, it's asking for the shape of the molecule. So it doesn't really give you a shape right here. The way this would be drawn correctly is like this. And we'll take a video on that later on as well. This is more like general chemistry, more than basic chemistry, but you know, it gives you a good idea. So the reason why we know it's formatted like this is because carbon is most of the time going to be the central atom when there's a molecule. So it's central right here, and we can put the other 3 elements on the outside. Now, if we look at this from the side, there's some elements that are going to kind of be like this. Like, I don't know how to explain it. It's kind of complicated. Let's just say there's elements that look kind of like a pyramid, like that. And there's some elements that, if you turn them on the side, just look like this. They're planar. So in this molecule, there's no specific force making carbon go up right here because there's no 4th atom here. This would be a different story though if there was like this shape or like this shape. But right now we're just looking at this really basic shape, and let's just remember trigonal, triangle, and we said it was planar. So the answer here is going to be trigonal planar. I know that might seem confusing right now, but there's going to be a video on it later on. This question is also for another video. It's about dissolving and polar and nonpolar molecules, but water will dissolve polar molecules very easily, and we'll go over that later on. Okay, so this is the last question I'm going to do in this video. We'll go over chemical reactions and balancing reactions in our next video, but this is how to convert moles to atoms to grams and such. So I always remember the AMG. A stands for atoms, M stands for moles, and G stands for grams. So it's asking to convert 96.00 grams of O2 to moles. So we have grams and we're going to moles. This is a very simple equation. We're going to use a box method. So we're trying to cancel out grams, so we're going to put grams on the bottom here. Grams of O2, and we're trying to get moles. So moles are going to go on the top right here. So what we're going to do here is find the atomic mass of oxygen. When we look at the atomic mass of oxygen, we're going to find that the atomic number, or the mass number, sorry, the mass number is 16. However, we can't just use 16 for this because we have O2, not a singular oxygen. This is because O2 most of the time exists with 2 atoms as O2. So instead of 16, we're going to use 32 grams. And then, obviously, this equals to 1 mole of O2. And this is very simple. What we're going to do here is divide 96 by 32. and that should give us 3. And remember, we're looking at significant figures. The way we determine how many significant figures we have is by the original number we were given. This is going to have 1, 2, 3, 4 significant figures. 1, 2, 3 zeros makes it 4 significant figures. Answer is D. So I know that might have been a little confusing, but if you need any more additional help, go check out my website or my other videos on this channel, and that'll probably give you a better idea of where you're stuck. Thank you for watching this video, and I hope you enjoyed it and it was helpful.